Thank you for reminding me, by the way. So what I'm going to do is very quickly just go over what I did, like just 2 minutes. Please be patient. Meanwhile, people can think about how to prove it. So if you're watching this on YouTube or something, I'm sorry, we forgot to record the session till now. The point of this class is we're going to be discussing Hall's theorem. So I started by showing this sort of example, which dealt with, you have these sorts of square sheets with lots of polygons on them, and you have like kind of these pins, and you want to make sure that each of the pins passes through different polygons. And like the magical thing is that this is somehow equivalent to solving this problem where you want to find an injective function, or you want to pair up edges in some sort of disjoint manner. And like that is like impossible. Like we were dealing with simple geometry, and now suddenly you've gone to something entirely different. And that's what Hall's theorem really allows you to do. It allows you to go from like something which looks like a very reasonable thing to a entirely abstract sort of thing. And it just works so well there. So the question why Hall's theorem arose is, there were these sets of teachers and students, and they really and like you wanted each teacher to get exactly one student, but you didn't want there to be repeats. So like each teacher should get a different student in some sense. You want to match the teachers with the students. But there were some conditions, like the teachers only like certain sets of students. This teacher likes only S1 and I don't know, S2. This teacher likes others and so on. And the question is, can you make this sort of perfect matching where everyone is getting a different sort of person? And answers obviously not always yes, because just imagine the teachers just didn't like anyone, then you can't do anything. In fact, even if the teachers liked someone, it's very much possible that all the teachers just like the same student and nobody else. So you won't be able to pair the other student. And then we saw that, even if each student is liked by someone, and even if each teacher is like someone, even then we can have issues. Because the idea is if you have this sort of W, which is like a subset of teachers, um, let's say there are three teachers here, but this teacher likes this one and this one, this teacher likes this one, and this teacher likes this one. So all in all, these three teachers together, they like only these two students. So if in general you have like five teachers who together like only four students, all the best. You won't be able to make a perfect matching out of it, obviously. So like one observation that we have made as a result is that every subset of teachers, you should have that the neighborhood, that is the number of students that are together liked by that subset, should be as many, have at least as many as the original. So yeah, that's fairly understandable, I feel. And like the point is basically that you like no matter how hard you try, if you have five teachers who like together only four students, you just can't. So that's not very surprising. The surprising thing is Hall's theorem, which says that if this condition holds, that is, you don't have this sort of stupid contradiction, then there will be a perfect matching. And that's what we are about to start proving. So the idea for the proof is this sort of induction. The first idea that you can think of, is like you have five people, like just pair off the first person with, I don't know, whoever they like. Let's say for the sake, let's say without loss of generality, like first person like this person. Okay. And now I just try to solve the remaining. That works or maybe not. The issue is that, when you just pair off randomly, you might be losing this criteria. Like it's possible that there was some set W over here. I'll give an example. I need to come up with something good. Okay, let's do it like this. Yeah. So like the point is basically that this has a perfect matching because you can take this one, this one, this one, this one, this one. It's a very simple sort of thing. But if I take this first edge over here, now I'm stuck because I can't pair this with anybody, right? And like the issue basically became for us that when we paired this stuff up, we lost the criteria over these two. Like earlier, when we Not these two, sorry, rather this. Because when you paired this up, now in the remaining graph, this guy just doesn't like anyone. So you have NW is less than W. Yeah. So that didn't work out too well. But in the original graph, you had equality. Like if you took this one, they were adjacent to this. So it didn't really matter too much. So this is one sort of observation I have that, if this guy only likes this person, then that's really the only choice you have. So in general, if you have a set W of people and they together like exactly that many people. So these two sets have the same size. Then that kind of thing is very forced. You have to work with it like in a very specific manner. So in fact, let's say there is some subset, okay? There is some subset where this thing holds, like this one, where these two people together are adjacent to exactly two people. And, just for the sake of this thing, I'll add in a couple of extra edges here. Yeah, so here in these two things, there's exact equality. So what I'm saying is basically that you might as well solve the problem for these two and then solve the problem for these three, because there is no, like even if there was an edge from, I don't know, here to here, you would never use it. Because if you ended up using that edge, then you've given away one of your neighbors for this guy, and now you'll have like this, which is bad. So, I didn't explain that too well, but the point is basically that if you have the neighborhood size is the same as your original set, then pairing something from outside this W to your NW is really bad idea. So by induction, we solve the problem for these ones, and then we solve the problem for these ones. And the question can be, why don't we get a contradiction now? That's something for you to think about, actually. It's not that hard to understand why there shouldn't be a contradiction. Basically, you'll show that, if in this remaining three people, suddenly there is such a contradiction, then that means originally also there should have been a contradiction. That's kind of the thing you can prove, because you can say that, okay, I don't want to give away too much, but the point is if there is some subset S dash over here, which suddenly now after you deleted these two people stops working, that means that S dash union W in the original thing would also have one. Something for you to clarify and figure out the exact details. I'm not giving away too much because someone's on unmute. Huh? Is someone wanting to speak? Uh, who is it? I cannot figure out. Oh, right. Done. Okay, so that's the idea of the proof that, okay, we're not done by the way. We have shown that if there is some, such perfection somewhere, then you have to be careful and you have to solve that part by induction and then solve the remaining. Okay, what if this never holds? What if you always have this is bigger? Like we had shown that it's less equal. That's what we've assumed by Hall's criteria. But what if it's just less? So then the idea is you can actually do whatever you want for your first choice. Because if now there's a contradiction, that means that earlier there must have been equal. Again, I'm not going too much into depth, but the point is going to be if there's a contradiction for S dash, then take S dash union the thing you just deleted, and there you would have uh, equality, and so it would become a problem. So yeah, that's the general idea of the proof, that you're inducting, but in a really smart way. So you're being really careful on choosing your W, and that gives you the freedom to sort of um, make a few mistakes in some sense. And yeah, that's sort of how we proved this theorem. Let's really get into the applications now because people are probably getting quite bored by now. So let's take a simple problem to start off with. Hmm. Okay, we won't take the simplest problem actually. We'll take a slightly tricky one. Not very tricky, just slightly. Or actually, I'll take this one. Why not? Okay. Also, someone on chat. Try to speak up if you can, but anyway, I'll see. I have a question out of the topic. The proof using induction that NCR is a natural number for R between 0 to N. Okay. I'll answer this at the end of the class. Yeah, it's not too hard to prove this, but we'll talk about it at the end. Uh, okay. Meanwhile, this is our question. And if you can convince yourself that you are supposed to use Hall's theorem here, that itself, I think, is a big achievement. Also, is my voice clear to people? It's very late to ask this question, but I'm just asking because I didn't wear my earphones today. Yep. Okay. I think I'll wear them
Yeah, yeah.
anyways because I guess it's just more clear when I wear. Okay, I'll have to unentangle it. That's too much effort. It's fine. I think people can hear me. So, yeah, this is our question. The question says you have 12 candies. Already, I'm feeling a bit hungry. Arranged in a circle, four of which are rare candies. Okay. Chad and Eric. Wow, great names, I must say. Let's change the names. I'll say Rohan and Pranjal. Why? Okay, Rohan and Pranjal want to collaborate first. Okay, this is so much effort. I give up. Let's just go with Chad and Eric. Yeah. So first, Eric comes and is told which four candies are rare candies. Then removes four non-rare candies from the circle. Then he must determine. Okay. So the question is basically saying, you have like 12 sort of candies with you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And out of these, four of them are kind of rare, like I don't know, expensive or just not found a lot or whatever. That's- And they're not like, okay, they're not consecutive. Let's remove. The circle and all is like pointless, by the way. Like you can imagine them in a line or however you want. Let's say these four are rare, and then I know that these four are rare because someone tells me that these four are rare. But like my best friend does not know that. I want to tell that to him, but the only thing I'm allowed to do is delete four non-rare candies. So let's say I delete this one, and this one. So now when my friend walks in, what he sees is this, but he doesn't see the white. He only sees these eight candies arranged. And he needs to predict that the four rare candies are the ones that they were. So like he has to somehow figure out that there were these four, seeing only these eight things. So coming back to the question again, just one final this thing. You had 12 at the start, four of them were rare. You delete four non-rare. Now you're left with eight. Four are rare, but your friend does not know which four. So he only sees eight and he has to tell which four. And that's kind of like magical. So and the question says decide whether it's possible. I'm going to tell you yes, it's possible. Uh, and I've also indirectly told you that hey, the way to do it is Hall's theorem. But uh, until you see it, you don't see it. Yeah. So, any ideas on how we can approach this problem? I don't expect you to actually. If someone comes up, either they've already seen Hall's theorem before or something, because this takes some time to sink in, honestly. So maybe it's worth thinking about for 2, 3 minutes and even convince yourself that this could be possible. Because in an exam, honestly, I would spend a good half an hour at the very least trying to prove answer is no. Source of this problem. Good question. Let me quickly find it. I should have written sources. Actually, I will not tell you the source. I'll tell you after we solve it. Uh, yeah, I'll tell you after we solve it. I'll find it anyways. Okay. Yeah, I found the source. I'll tell after we solve. But yeah, you can trust me. It's like a real problem. I'm not trying to scam you. The statement is actually true. Um, yeah, legendary names though. Eric and Chad. Chad names. Okay. Any ideas? Like anything at all. Stupidest observation you've ever had, but observations are observations. Okay, I think I'm gonna give away a little bit on this problem because the first one is always the toughest. So, first of all, let's try to, do some math, some around quantitative analysis of what is going on. So, for starting off, how many possibilities are there for these sort of rare candies? 12C4, I think that everyone can agree on that there are 12 candies and some four of them are rare. You don't know which ones. But there are these many possibilities on what I see as which four of them happen to be rare. And then the question is, how many possibilities are there for what my friend sees? And what my friend sees is actually just eight candies. Like he doesn't see anything distinct about them. So he just actually just sees, I put nine. Okay. And he just sees eight candies. And those eight could be possibly any eight of the 12. Technically, not really, but let's just say that. Okay. 12 choose eight. And the first observation, can anyone tell me what is the observation around these two numbers?
Yeah, the same.
Exactly. That's same. Because 12 NCR is NCN minus R. So that's quite a cool this thing that basically the number of possibilities for what I saw is equal to the number of possibilities for what my friend sees. So essentially for every possibility of what I see. So I see one of these 12C4 things and I need to map that to one of those 12C8 outcomes. Like more formally, basically what I see is like um four of the things are circled and the other things are like normal. And what my friend sees is like eight of the things and nothing else, and essentially sees that the other four are taken off. So each of these things has to map to one of these things. And if we can manage to do that, basically that would mean that every time he sees something over here, he can like kind of reverse our process and he can go back and see that, okay, this was the thing that should have led him to this. So yeah, that's basically our point now. Do people see how matching is coming in now? No? It's okay. It's okay if you don't see it because it is tricky. So what I'm going to do is, let's say there were only three candies, and one of these is one of them is rare. Okay. And what you do, let's say you see that the third one is rare. You have to delete one of the other two. So the other guy comes and sees one and three, and he has to reduce that the third one is what is rare. So I'm going to write that in a more formal way. So what you see is one of these things. One, two, three, one, two, three, one, two, three. And either the first one is rare, or the second one is rare, or the third one is rare. One of these. This is what you see. And then the question is, what can your friend see? Your friend either sees one, two left, or he sees one, three left, or he sees two, three left. And the idea is that one, two can be left if I delete three from here. So let's say I delete three and now I would be at one, two. So it's possible to go from here to here. So I'll just join them. Similarly, it's possible to go from here to here because I can again delete three. But it's not possible to go from here to here because I can't delete the one which was actually right. So we don't have this third edge. Similarly, 1, 3 is connected to this one and this one, but not this one because I can't delete two. unless I mess something up. Yeah, yeah, I got it. And similarly, 2, 3 is connected to this one and this one. So this is sort of our thing. And basically what I'm going to do now is I'm going to make a perfect matching in this. So this is connected to this is connected to this, and this is connected to this. So point is, if he sees 1 comma 3 left, he will guess that the answer was 3. If he sees 2 comma 3 left, he will guess that the answer is 2. And if he sees 1 comma 2 left, he will guess that the answer is 1. And on the other hand, when I see one is the special one, I will go to this one so that he manages to guess correctly. If I see this, then I'll go here and then he will go back. Got it. And that's the whole point. You're basically mapping each of what he can see to one of your nice things, and it all works out. Do people understand this?
Yes.
Okay, cool. So it's a similar idea for the 12 choose 4 thing also. Again, you have 1 to 12 written, and now 4 of them are highlighted. So you have like much bigger list of things over here. And on the other hand, there are 8 things. Again, you have a much bigger list. And now some pairs are connected if you can delete some things from here so that you end up at one of those. That's kind of the point. And you want to make a perfect matching in this graph. So you want to say that, okay, if you see this, then you go back here. And if I see this, then I go here. So we have like this predefined strategy. So all we want to show is that this graph with 12 choose 4, how much is 12 choose 4, by the way? Someone who's willing to calculate. Um, it's like 11 into 10 into 9 by 2. 11 into 5 into 9. That's what? 495? Yeah, 495. So you have like earlier we just had 3, so we could just do it manually. We found a perfect matching. But now we have 495 things over here, 495 things over here, and lots of pairs of things are connected. How are you going to manually find the perfect matching? You can't. So instead, you use Hall's theorem. You show that for each set of things over here, they're connected to at least as many things over here. So the matching has to exist. I'm not telling you what the matching is. I'm just telling you that it exists. Finding it is your job. So yeah, all that is left for us now is showing that this sort of matching exists using Hall's theorem. So let's take a random set, okay? Let's take this set S of other W because we were using that, and let's try to figure out what its neighborhood kind of is. First of all, can we figure out how many edges exist from this point to these places? Like earlier we saw that 1, 2, 3 can lead to this one or this one, like 2. Similarly, 1, 2, 3 can this one can lead to this and this. So each thing was leading to exactly 2 things. The question is, how many things does it lead to over here? And that's a bit of counting, a simple count actually. Can someone answer this? So essentially you see, let's say 1, 2, 3, 4 are highlighted. Now the rule is that any final 8 things that can be there, they must have 1, 2, 3, 4 in them. Because you're not allowed to delete one of the rare candies. So you're only allowed to delete the others. And you should end up with 8, and you already have 4. So you want 4 more out of these 8. So how many ways are there, people? Come on, answer up.
84.
Exactly, 8 choose 4. So each of these things has 8C4 edges to stuff. And on the other hand, if you see 8 things right now, how many original possibilities could there have been? Like basically the original possibility would mean you're adding back the ones that are missing. But from among the eight that you can see, some 4 of them are uh, rare. So let's say you see 1, 2, 3, 4, 5, 6, 7, 8. It's possible that 1, 2, 3, 4 were rare. It's also possible that 5, 6, 7, 8 were rare. It's possible that I don't know 1, 2, 4, and 6 were rare. So again, you basically have 8C4 sort of possibilities for which ones of these were the rare ones. So what I've basically proven is that you kind of have like lots of, you have 12C4 things here, and you have 12C8 things here, which is the same value actually. And each of these, the degree, that is the number of things it's connected to, is 8C4. And each of the things this guy is connected to is also 8C4. So everything in our thing is connected to the same number. And that's a very useful thing. So there's actually a general theorem which says that um, if everyone has same number of edges, and not zero, because that's dumb, um, then there's a perfect matching. In the bipartite graph, uh, in uh, s- in a union of two things. Yeah, so basically, yeah, exactly what we had here. But I'm basically saying if you have n things here and n things here, and each thing over here is connected to d things over here. This also is connected to d things. This also is connected to d things. People here are also connected to d things, etc. Then this thing will have a perfect match. So this is what we are looking to prove now. So here's where Hall's theorem comes in. And we assume that, let's take some subset W. So you have, let's say you take the first one, the second one, and the fourth one. And let's say for the sake of contradiction, these guys are only adjacent to two people altogether. Something like this. Like there is no other edge. So the idea is that, we know D edges are coming out from this one. We also know D edges are coming out from this one. We also know D from this one. But the issue is we are not getting 3D totally, because some of them might be overlaps, like this, right? Because D is this, the D may say one, you're counting for this and this. Like the point is that there are not 3D things over here. They are much lesser. But are there enough is the question. And okay, one other useful fact is that these guys also have D things. So yeah, now we need to somehow show that you are somehow having as many things on the right side as on the left side, even though these things were overlapping, so you can't really use that directly. Any ideas, people? Okay, again, this is quite hard to come up with first time, so I don't blame you for not being able to think of it this fast. And this is a very useful thing. So, in fact, as useful as Hall's theorem is, half of the problems that use Hall's theorem just end up using this, because you end up having that everyone has the same degree. So it doesn't really matter. Like you can, rather than even proving this thing, you can directly state this, which is, I think, called Koenig's theorem or something. I'm not sure. Uh, but yeah, so okay, let's just do the proof, right? The point is, we know that stuff is overlapping, I agree, but if you consider these three things, there are 3D edges coming out, right? There should be uh, D from this one, D from this one, D from this one. They might go to the same people, I don't know, but there are 3D edges coming out for sure. And okay, in general, okay, let's just say 3D. And on the other hand, these two people, let's look at them, right? Now, there's no one saying that this guy can't be liking this third person also. It's very much possible that you have something like that. But um, the number of edges that are coming from here are definitely at least the total number of edges that are going here. In some sense. Okay, how should I frame this? It's like you had 3D edges coming this way, So all of those 3D edges are taken in by these two, kind of. Like you have 3D edges going, and they're not going to anyone other than these two. So everything has to go to one of these two. So the number of edges that these two people receive is at least 3D. But we know that the number of edges they receive should be exactly 2D because there are two people on each head. In general, what I am trying to say is that if you had, a subset, if you take a subset of k people over here, and that's connected to, I don't know, k minus 1 over here, there should be at least kd edges going this way. So that means that these k minus 1 people, they have at least kd edges coming their way. But there should be only k minus 1 into d edges coming their way because each one was supposed to receive exactly d things. So we have basically shown that k minus 1 is at least k, which is kind of sad. Um, so yeah, that is the proof. Is it clear to people? If not, I can go over some of the details again. And feel free to say whatever questions you have or anything. Like,
Yeah.
yeah, meaning clear? Okay, also, by the way, the source of this problem was some PureMac 2016. So yeah, this is a very cool problem on Hall's theorem because you can't actually find the strategy very easily, but you can show the existence using this sort of perfect matching idea. And I think the few key takeaways from this problem are one, definitely this theorem, which is just so useful because it comes up a lot. And apart from this, it's also useful to remember this sort of idea that when like how do we think of Hall's theorem here? That's the question, right? The idea is that you kind of want to match. There are like two sorts of things that are there. One is what you see, one is what your friends see, and you want to match them, right? Kind of like you want to pair things up. That's sort of the intuition behind why you want. And first problem you do that doesn't feel clear at all. Second, slightly unclear. But as you do 4 or 5 problems, it becomes very clear that, okay, this is what we were looking for. So it's all about doing those problems. And my hope through this class is, we do some of them and then you try a couple more on your own. So we could get somewhere. Um, let's take another problem, which is slightly on the more easier side. I think I took a one which was a bit too tricky for the first one. Okay, let's take this. And this one I think is just a classic problem. Like I don't even think it has a source as such. Okay, so yeah, if people don't know how playing cards work, it's like you have 1, 2, A, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, does not matter. We just think of them as 1 to 13. And there are also 4 suits. So there is 4 of them, clubs, etc., hearts, diamonds, and all. But we think of them as A, B, C, D. We keep things simple. Okay. And in fact, suits barely matter to us. The point is basically that you have basically split these 52 cards. There are 13 in each sort of suit, and there are totally 52. And you've split these 52 into groups of 4. And a very simple way of splitting them into groups of 4 would be, put all the ones together, put all the twos together, threes together, etc. But you're not being so nice. You're being random. 1, 2, this. But in fact, like you could take all from the same suit also. Like it could be anything. You basically split it in like 52. You're splitting that into lots of groups of 4. It's like, I think the notation for that is like 52, 4, 4, 4, 4, 4, like that. I'm not sure. Something like that. So there are lots of ways to do it. We're not looking into how many ways we have to do that. But the point is that now that you have these groups of four, you want to take one card from each group. So that what you end up with is one card of each number. So you end up with 1, 1, 1, 2, 1, 3, 113. Like it doesn't have to be all of A, ace, all of A or all of the B suit or whatever. You basically, I'll give a simple example. I'm not going to write everything down, but like, okay, maybe instead of 13, then I can show you with 4, right? Or 5. Is 5 too much? 4, 4. Let's do 4. So you basically now you have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. And I'm going to put these into groups. So like 1, 1, 3, 4, 2, 3, 1, 4, 1, 2, 2, 2. So twos are done, ones are done, 3, 3, 4, 4. You've been given these four sets, and you want to pick one from each so that you end up with 1, 1, 1, 2, 1, 3, and 1, 4. So how I could do that is, I think you can do 2, 1, 3, 4. Aha, you can do that. That's cool. Um, and the even cooler thing is that once you have done this, these guys are gone now. You can do it again with the remaining 3, 3 in each. So what you can do is now, uh, uh, you can do 1, uh, 2, 3, 4. Aha, we're done again. We delete them. Then you can do it another times. So again, you do 4, 2, 1, 3. Aha. And then you will be left with 1, 4, 2, 3. Magic. So you can like keep doing this again and again. So that's kind of very interesting. And like the main point of the problem is doing it once, because after that you can just induct. Because the point is like you had like um, basically you had 1, 2, 3, 4 coming 4 times. That 4 is kind of stupid. That's just because cards may you have 4 suits. Even if there were 100 suits, then you would basically have 100 cards in each set, and then you would have to do the same thing. So it doesn't really matter. But um, yeah, the whole question is how do we take one card from each set while following this? So the first guess would be, why don't we try some sort of greedy sort of thing, like just take the first one we can find. So let's take this, and take the next two we can find. Okay, and let's take the three we can find. And oh no, where do we take four from now? Because there's no four over here, so we're stuck. And okay, let's take a step back. What if I took a 2 from here instead? Then I take a 3 from here. Oh, that works. That's lucky. But I mean, the thing is, it's like very random. Like sometimes it'll work, sometimes it won't. Like, what if I try to do uh, you get the idea, I think. Like the point is like it seems to work usually. Like you can find the answer fairly quickly, but there's no very formal way to figure out how you're going to do it in general, because you are possibly getting stuck. And then those points you are going back and you're fixing your mistakes. But while fixing your mistakes, you're basically making random guesses. So if your first guess didn't work, what's the guarantee that the second one will work? And if your second one doesn't work, what's the guarantee that you have any guess left to make? So, yeah. Also, some people left or what? Suddenly. Can people hear me?
Yes.
Okay. I do not see why people left all of a sudden, but okay. Yeah. So the idea is basically that you want to pick 1, 1, 1, 2, 1, 3, 1, 4. So you want to kind of match. Let's say this is set 1, this is set 2, this is set 3, and this is set 4. So you want to match each of these to a number from 1 to 4. Do you want to match them? Wait, let's go back to the 13 one actually, because it's a bit confusing here because you have 4 and 4, so it's a bit weird. Rather what you want to do is yeah, it still works. Okay, you have 13 groups over here, and here you have 4. Okay, let's stay with 4 sets. Who cares? So you have 4 sets, S1, S2, S3, S4, and you want to map each of them to a number from 1 to 4. So like S1 can be 1, S2 can be uh S2 can be 3, let's say, S3 can be 2, and S4 can be 4. That works because S1 has a 1, S2 has a 3, S3 has a 2, and S4 has a 4. So it all works out. And the more general thing is, um, like, who all are we connected to? For example, S1 is connected to 1, so you can go to 1. You can also go to 3, and you can also go to 4. S2 say you can go to all 4 actually. S3 say you can go to 1 or you can go to 2. And S4 say you can go to 3 or 4. So this is kind of your thing. And you want to make a perfect matching here. So well, I told you earlier that that every actually let's go to S13. I'm so sorry because here everything is connected almost. So the point is like if you have 13 sets of 4 instead, and you're mapping them to numbers up to 13, now still each guy is connected to at most 4 things because let's say your S1 was 1 to 7 and 11. So S1 would be connected to uh, 1 to 7 and 11, something like that. And then S2 could be connected to some 4 other things and so on. So we're almost done, because we have 4 things. Every set is connected to 4 people, and each one can come from 4 sets. But we have an issue, which is this. Like, we are not connected to 4 things here. We're only connected to 2 because there's a repeat. 2 is coming twice. So it's not necessary that life will work out in your way. What if you had something like 1, 2, 2, 2? Now S1 is only connected to 1 and 2. We don't have 4 edges. If we had 4 edges from everything, we would be done because we would find a perfect matching and game over. But now what? And this is the part where, convincing yourself that your next step is legal is pretty challenging. Like you need to really, okay, there is a way to frame it without what I'm going to do, but I just think this is a lot more instructive kind of. So the idea is, I'm connected 3 times to 2. Why have you made only one edge? Let's make one more edge between the 2 people. Make a one more edge. So this guy is connected to 4 people. It's just that it's connected to 2 from the same time 3 times. Okay. But the point is that does not matter. In when we did the whole Hall's theorem thing, and we did this thing, and we did everything, we never really used the fact that every edge was only one time, kind of. Like you could always have the same edge being used 2 times and it would still work. Like for Hall's theorem, you can imagine why the proof should be the same because if there are 2 edges, then I mean just ignore one of them because it doesn't give you any new information about the neighbors. So um like Hall's theorem is undisturbed by whether there were 5 edges between these two or 4 edges or one edge because the neighbors are only the ones who you have at least one edge to. Whether you had 10 of them or only one of them, it does not matter. And here is where this theorem is where stuff starts changing. So, but still the same idea works. Basically, the point is 3D edges are going to come out and only 2D are going to come back in, which is what is happening even if you have three edges to the same thing. So you can actually imagine this if you've heard of the term multigraph, where you are allowed to have two things connected by the same thing in multiple ways. Like sometimes, basically there's graph theory where you can imagine things as roads and cities, and these are like edges are like roads between different cities, and you can imagine two different roads between the cities. So that's like multi-graph. But graph theory isn't really relevant here, so we're going to ignore it. And we're just going to do the same thing. Now everything is exactly four edges coming out of it. And each thing is inputted, like, is received by four sets. It could be the same set four times. Like, your set could just be 3, 3, 3, 3. And in that case, you would just have four edges like this. But it does not matter. And that's like a really cool thing that, it feels very counterintuitive that that should matter because that's only one edge. You can't fool me by saying it's four, but I can. And if you are a bit unconvinced by that still, I recommend you go through this thing again and try to prove it given the condition that it was a multi-graph, that there could have been multiple edges, and you'll realize that nothing changes. You don't have anything different to prove. So um, it's the same thing. And yeah, once everything has four things coming into it and four things coming out of it, now you just know that there is a perfect matching. And so you're done. Um, so the point is like if you have a perfect matching, you can use that perfect matching, delete one of each. And the cool observation is once you delete a perfect matching from such a special graph where everything had degree 4, 4, 4, 4, now everyone's degree has got reduced by 1 because I paired up this one and I deleted this edge. It's become 3. This also became 3. Everything became 3. And these ones also became 3. But it's still a regular graph. This is called regular, where everything has the same number of edges. So if it's regular, I can do it again. So I can make it 2 now. And then I can do it again and I can make it 1. And when everything has one edge out of it, that's basically a perfect matching. So at that point, we would be done. And that's what I was talking about earlier, where we were, deleting one set and deleting a second set and so on. But yeah, I hope that was clear to people. Was it? If not, I can go over some stuff again. And feel free, people, to like say that, hey, that didn't, I didn't get it at all. Can you go over from the start? Okay, I take silence as a, I'm not so sure, but I think I'm getting it. Because that is me when I was, first learning these concepts. So I can relate to this feeling of like understanding it, but not believing in it. That kind of thing. And okay, I don't have too much time left. There is one idea that is like really, really important, and I want to do. So I'm going to do it. It's probably the easiest problem actually. And I keep saying this for each problem. I don't mean to say that the problems are actually easy. Like it's just I feel after solving the previous one, this one is comparatively better. Okay, sorry, I am back. Yeah, this is our problem, the third one for now. And yeah, so basically we have like a chessboard and uh, it's an 8 by 8, just imagine. And basically the point is that each row and each column has exactly, I don't know why I used n here. I feel like k is just a much better letter to use for this sort of situation. But okay, let's imagine k is 1. So basically, maybe k is 2 rather. So each row has like two things colored, something like this. And this thing also has two. So this has two, 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 etc. Every row and every column should have two things that are colored, or K pieces have been placed. It's the same sort of thing. And you want to basically choose 8 pieces such that no two of them are in the same row or column. So you want to like pick this one, this one, this one, this one, something from here, something like that. So that there's no like, if you know how rooks move, basically no rook can capture another because they're not in the same row or same column. So yeah, that's kind of the idea here. And yeah, again, it's going to be Hall's theorem to our rescue. And the whole idea of this problem is something that comes up a lot, which is thinking of a grid as a bipartite graph, which is like basically you have these rows and you have these columns. And like you think of row 1, row 2, row 3, all the way till row 8. And you think of column 1, column 2, all the way till column 8. And you join these two with an edge if there's a piece in 1 comma 1. So like I've made like a grid sort of. This is 1 comma 1, this is 1 comma 2, this is 1 comma 3, and so on. This is 2 comma 1, and so on, etc. Everything in this grid is now labeled. And but only some of these labeled points have pieces on them. So for example, this one has one, or this one has one, or this one has one, something like that. You have this sort of bipartite graph, and you want to do stuff with it. So the idea really here is going to be is first, okay, how many red edges are going to come out from this one? We know that, okay, in each row there are 2 pieces or k pieces. So we know that this row will be connected to k columns in which there will be pieces. So this guy has degree k. This guy also has degree k, k, k. And also by degree, I mean like number of people you're connected to. And similarly, this guy also has degree k, degree k, degree k. Everyone is degree k. Boom. And we're already done. Because now what this means is we have a perfect matching. And what a perfect matching does for you is basically you're pairing up rows and columns so that there's no repeat. And now it's something like, let's say your perfect matching gave you 1, 1, 2, 4, 1, 1, 2, 3, 4. Okay, I'll actually just do it till 4 because something like this. So what this would mean is you take this cell 1, 1, you take 4, 4, you take 2, 3, and 3, 2, like this. And these four no two share a row or column because like that's how we made it. And it all works out. And again, also we can delete these k pieces, these 8 pieces, and now there'll be k minus 1 in each. So we can do this again. So that's a pretty cool thing. And this idea is kind of hard to come up with the first time, but as you go on, this will come up so much. But if you don't see it coming in a problem, that'll be kind of something to be sad about. Because essentially, whenever you see this condition, no two of them are in the same row or column. This is literally telling you this is Hall's theorem. This is bipartite graph on rows and columns. You have to do it. There's going to be no problem where they say this, but it's not Hall's theorem. So yeah, that that is one of the things here. Um it's okay if this, by the way, is going a little bit over your head. I feel like this Hall's theorem is something that kind of takes some time to settle in. You need to give it a lot of practice and time, and it's definitely not something you can learn in 1 hour. But uh, I don't know. I'm trying my best, and hopefully, um, it'll help you also. So yeah, till now every question we have seen is actually this very special case of Paul's theorem, where everything has like the same degree. But that need not be true. Like you need not have the same number of edges from each thing. And let me see one question on that. Okay, actually, instead of that, let's do this problem. No, uh, I'm confused. Yeah, let's fine. Let's do the one I showed at the very beginning, the geometry one. This will probably be the final one we do today. We have like 10 minutes. So I'll give you people a bit of time to think about this. Uh, yeah, okay. I see someone is unmuted. Do you have some idea on this, or did you unmute by mistake, or you have some question? Okay. Yes. Thanks. 2023 polygons. So basically, you're given like a square sheet, and it's split into a lot of polygons in some weird shape like this. Like polygons are basically like, straight lined figures in some sense. That's a very bad definition. But basically, each of these has area one. That's the main thing, even if it looks like that's not true. All of these have area one. And then you have another sheet where this has been done again, but in a different way. So something like, I don't know. In fact, you'll see that, straight lines are not very relevant. Like any sort of curve also, if you make, so that all the things have area one, it still works out. Yeah, it can be square, hexagon, anything. Like the full thing is a square, but inside it can be anything. And it need not be regular. It can be as curved, tilted, can even be circles, honestly. For the sake of the problem, we don't consider that. And also, I feel like if you make it like any shape, it's kind of like hinting you towards the solution. If you give polygon, that's kind of misleading you in the sense that you think that the geometry is actually relevant, but it's not. Um, yeah, so you have like two things and they're put on top of each other, and then you place pins. The point is, if I place a pin right over here, then there'll be a thing equivalently over here also. If I place something over here, equivalently that will be over here. If I place something on the top left, that will become over here. So I want to place 2023 pins so that each of the 2023 polygons on this guy gets covered, and each of the 2023 polygons on this guy also gets covered. So in some sense, I kind of want to match these things. Basically, I want to pair this polygon with, I don't know, this one, and put a pin so that their intersection has one, and I've gotten those two, and then I match some other two polygons, and I match. So there are 2023 polygons over here and 2023 over here, and I want to match them in such a way that I can place pins. So um, it seems obvious to you? Yeah, so if you're thinking of the thing, the point of the problem is that, you know, when you place something at the top left here, it's automatically also at the top left here. You can't put points separately on the two things. Like, uh, the issue becomes that, okay, you place a point over, you place a pin over here, and that goes inside here, and then you try to place a pin here, and that also goes over here. So you got two pins in the same polygon, and that will be bad. So you need to make sure that they're different in different polygons on this one, but they're also in different polygons on this one. And that's non-trivial because their shapes are completely independent of each other. Do you see why now? Or does it still feel like it should be very easy? Okay, cool. So the point is, we have like, we're basically trying to pair these 2023 polygons with these 2023 polygons. But we can't pair anything with anything, right? We can't pair this polygon with this one. We have to pair it with, I don't know, either this leftmost one or maybe this one. If you can place a pin right here and that falls right here, something like that. And um, so each polygon is like kind of forcing you to, like this polygon says, I can only be paired with these guys. Like, I don't know, some of them. And similarly, this polygon says I can only be paired with these ones, and so on. So it's like a perfect matching sort of scenario where you want to make a perfect matching and you want to join these sorts of things where a pin can be placed. So yeah, the question becomes, can we prove Hall's theorem? And if you notice now, the same degree thing is definitely not going to work because what can happen is like you have like one sort of polygon here, it's the area one. And then on the other one, which is on, if I'm imagining is like overlaid on this. Like it's very much possible that it's like lots of polygons ke saath it's overlapping. So it's like there are edges to lots of things over here. But it's also possible that its edges are to exactly one thing because they're just like the same polygon on both of them. So both sorts of possibilities are possible. So we don't have the same degree anymore. So I think we're just going to have to go to Hall's criteria and say, okay, let's take a subset of uh, polygons, right? Let's take this one and this one. So totally I get like this sort of shape. And I want to show that if I if I overlay this shape on this one, like something like this, there are at least two polygons that fall inside this sort of thing, if that's making sense. Um, and yeah, it's a little bit hard and confusing because it's hard to imagine things on top of each other and all. But yeah, that's basically the point that, you know, if I'm taking one polygon here, one polygon here, one polygon here, and I want to see together these three people, how many things are they connected with? That's equivalent to seeing how many polygons on the lower thing these people have the smallest of overlaps with. Like even any overlap works for me. It just has to be an overlap. So like something like this, if you have like that. So like all of these red ones, this one, 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 this one. All of them are good with you. You just have to hope that there will be at least as many red ones as you took blue ones. And here comes in one condition that we never used. Hmm. So yeah, the question is how can we use this fact that if you have taken k polygons from here, their total area is going to be k, the blue ones rather. So maybe this. So if let's say for the sake of contradiction, that at most k minus 1 guys they are adjacent to, that would mean that this total red area is at most k minus 1. But we know that the red area is at least the blue area, right? Because everything within the blue area we're covering and little bit outside of it also. Because if some polygon went outside, that's fine. But anything that's inside is always a part of some polygon. So that is always going to be covered. So you're basically again saying k is less equal to k minus 1. Boom. And we're done. So yeah, like the takeaway from this problem, I feel is like um sometimes this is very important to go back to the actual statement of our theorem. Say it. Okay, let's say there's a subset of k people. Let's say what happens, what k minus 1 things are there. And you have to get a contradiction. It just has to be there. Because if you don't, that means that the either the problem is false or it's really hard or something. So, and yeah, it worked out quite nicely for us because we got that the blue area is at least k, but the red area is at most k minus 1. But that's yeah. So yeah, I think that's mostly the things I plan to cover today. Um, just a broad this thing of what we saw. We solved this problem finally. We saw how these random polygons are actually convertible into this sort of. What I used there was this sort of terminology of injective function, where basically I'm saying that I'm kind of mapping this guy to one of these people, this guy to one of these people, so that two guys don't map to the same person. That's what Hall's theorem is basically saying. And in fact, Hall's theorem can also be applied if you had lot more people here. It just won't pair everyone. Um, or no, actually, it can be applied if there are a lot more people here. It just won't pair everyone of this side, it'll just pair some of them. But everyone from here will have a different person. So it's an injective function. It's not surjective because some people are left out, but it's still injective. And if there are equal number of people as we've seen in all our problems, then yeah, then it's just going to be a bijection or whatever. So yeah, I think that is it. I'll stop recording. Uh, Ayush.